Hello, so let's continue to work on the gear train. And last time we introduced the basic concept of a gear train. Basically, it's a pair of external gears. So we mentioned that for a gear, the main concept for a gear is we need to make sure the contact point, because there's no steeping between these two gears, so the contact point for link 2 and link 3, they must have the same speed. So here, if we say the contact point is P, and we say VP2 equals VP3. And because VP2 we can express as omega 2 and R2. VP3 is omega 3 and R3. R2 and R3 are the radius of these two gears. And omega 2 is a rotating speed of these two gears, so they must be the same. So if you follow this equation, you can get their speed ratio. Omega 2 over omega 3 is R3, R2. And because for this one, if it's a pair of external gears, you can see the direction of the rotation is going to be opposite for this pair. Yeah, if omega 2 is rotating clockwise, then omega 3 is rotating counterclockwise. So you may put a negative sign here. Yeah. When I write this equation, I didn't put any absolute value. So actually, but you can observe it because, yeah, according to their arrangement, they should rotate in a reverse direction. But usually when we look at the gears, we don't usually use their radius. Instead of using radius, we usually use their teeth number. So teeth number means how many teeth are on this gear. So for example, this one may have maybe about 20 teeth, and this one, I don't know, this one is much more. So we usually use the teeth number instead of radius, and because they all must, in order to make a pair of gear, they mesh, and we need to make sure the teeth size is the same. If a teeth size is the same, then the number of teeth is just a proportion to the radius. The larger the gear and the more the teeth number it must have. So that's number of the teeth. So this one is for the external gear. So that's the most commonly seen gear. Yeah. For external gears, so their speed ratio is the inverse of their number of teeth ratio. Any question for this one? So we can take a look at the second case. Second case is a regular gear, an external gear, and mesh with another internal gear. So you can see that's the actual picture for an internal gear. So the smaller one is an external gear. The larger one it looks like a ring. and the official name is internal gear. Yeah. So for internal gear, it should follow the same rule. The contact point should have the same speed with respect to link 2 or link 3. You still need to follow this relationship, yeah, because there's no steeping between these two gears. Yeah. So the linear velocity of this point P must have the same speed when you see link 2 or when you see link 3. Yeah. But the major difference between these internal gears and the external gears is when you take a look at this one, if I'm saying omega 2 is rotating clockwise, then the ring will also rotate clockwise. So they will rotate in the same direction. So for external gear, omega 2 over omega 3. Because they rotate in the same direction, so we don't put a minus, a negative sign in front of it. So it must be positive because they indicate they are rotating in the same direction. So the major difference between these two is the direction. Yeah. Otherwise, we use the same expression to indicate their speed ratio. Any questions so far? And there's another type of gear, we call it bevel gears. Bevel gear, well, basically the calculation is the same. They contact a certain point here, and the point with respect to link 2 or link 3 must have the same speed. So still VP2 equals VP3. But the difference for this one is we can have a certain angle between these two axes. For this case, the external gears and these internal gears, their axes are all in parallel. But sometimes we need to make the input and output, they form a certain angle, so we may choose bevel gear. And the calculation there's no difference in the calculation. The only difference is for your application. In your application, if you need to make the internal, your input with an angle with the output shift, then you will use a bevel gear. Otherwise, it's the same. And another extreme case, this one is not bevel gear. We call it helix gear. So helix gear is, I think I have a video here. So it's another case. It's when the axis of the input, suppose this one is the input and this one is the output. This one is also the output. The input shaft and the output shaft, they are perpendicular. In some application, we need to use this type of gears. Yeah. If we need to make the input and output, they form 90 degree. Yeah. And we call this type of gear helical gears. And there are two types of helical. You can see these helical curves, this part and this part, they are in different direction. Yeah. And we call this one the right-hand helical gear, and this one left-hand helical gear. Yeah. So when it's rotating, it looks like this. The shaft, input shaft, and the output shaft, they are perpendicular. So you're probably confused, how can I distinguish this one is right hand, this one is left hand? Well, the basic idea I'm not sure if you pay attention to the screw, the everyday use screw. I think most of the screw is a right-hand screw. Right hand means when you rotate in this direction, the screw is gonna go in. Yeah. You can go home and to take a screw to investigate that, to observe it. And see if the screw you rotate in the right-hand direction, it's gonna screw in. Then that one is right hand. If you need to use this direction to make it screw in, then that one is left hand screw. Now for this one is we call it right hand screw. So imagine that's just a regular screw. If you rotate along my right hand direction, this one is gonna go in, right? If I rotate this one, I think right now it's rotating. Yeah, right now it's rotating in my right hand direction. Imagine if this one is a screw, it's gonna go in. Any questions so far? Or I can draw a. So for right hand screw, we may draw in. So what's this? So this one is a right hand screw or right hand helix. Yeah. So if I rotate, it's gonna go in according to my hand direction, right? If I rotate, yeah, according to my right hand direction, rotating this way, it's gonna go in. Imagine it's a screw. Yeah. So if I am using this right hand helix, so right now it's a gear, and I'm using this one to drive that gear. So the gear it looks like this. So right now, if I'm rotating according to my right hand direction, which direction should this one turn? Should it turn counterclockwise or clockwise? If I'm, yeah. How do you think? This one? Yeah, should be this one. Because if I rotate this one, so you take a look of this bolt line. If I rotate according to my right hand direction, how is this one gonna move? This one gonna move in this direction, right? If I rotate in this direction according to my right hand direction, this line is gonna move to the direction of the arrow. So if this line moves here, that means it's gonna push this teeth to this direction. So it's gonna rotate in this direction. So that's the same as the animation. Okay. Take a look of this one. Sorry. Sorry, no. Sorry, if I rotate in this direction, it should move in this direction. Sorry for a mistake. It should move in this direction. Because if I rotate in this direction, and this point is gonna go up, right? So if this line go up, it's gonna move here. If you take a look of this point, not sure if this one is. If I'm rotating according to my right hand direction, this point is gonna move up. If it's moving up, then this line is gonna become this line in the next moment. So sorry, I was wrong. So it should push this gear in this direction. Yeah, if it's rotating, maybe you focus on one line, focus on this one. This one is going up. So this white one is going to move to the yellow position. So if it's moving to the yellow position, then it's gonna push the teeth in the counterclockwise direction. Sorry about the mistake. So this one is right hand helical gear. So this one is a left hand helical gear or helical shift. So you will do the reverse. If there is a gear here, just draw the gear tooth here. So if I also rotate this one according to my right hand direction, then this line, if I take a look of this one, if I also rotate in the right hand direction, then this point is going to move up. All right, so next moment, this original white line also rotate in the right hand direction, and if this one rotating, and this point is going to move up. So this white one is going to become the move to the yellow position at the next moment. So in this case, it's going to move in this direction. So it's a reverse when you compare with this one. Yeah. But right now, because in this video, you put this gear in the bottom. So if I put this gear in the bottom, it's gonna rotate in this direction. When you put it on the top or on the bottom, they will rotate in a different direction. You can just imagine, you focus on one line and imagine how this line is gonna go at the next moment. Then you can distinguish which direction is going to move. Now, right now, this right hand one and left hand one, they're rotating in the same direction because one is put on the top, one is put on the bottom. So that's why they are rotating in the same direction. If I move this gear to this location, then these two, they should move in, they should rotate in the reverse direction. Any question for this one? Okay, so let's move to the next one. So why do we use gear trains? Of course, it needs to serve some purpose. And if you just take a look at this equation, you can see, well, obviously the gear train can help us to change the speed ratio, to change the speed from the input to the output. And if you still remember, previously we say, suppose there's no energy loss during the transmission from input to the output. If there's no energy loss, then the power from the input and the power to the output should be the same. So imagine we are considering a pair. Let me erase this. So imagine we're considering a pair of external gears. We say the input energy should be the same as the output energy, or the input power should be the same as the output power because of energy conservation. Yeah. If there's no energy loss, then this one should be valid. And what's the input power? If omega 2 is the input, power is the force or the torque times the speed. So right now we are using a pair of gears. We know the speed ratio is going to be different. So once you change the speed difference, once omega 2 and omega 3 they are different, the torque will also be different. And the ratio between the torque is the inverse of the ratio of the speed. So usually we don't only we use a gear train. The main purpose is usually not to increase or decrease the speed. More often we use it to change the torque. Usually the motor cannot provide a large torque, so we will install we call it reducer. Reducer means we are going to reduce the speed. But once you reduce the speed, you are going to increase the torque. So, not sure if you pay attention to an electrical car. Most of our electrical cars, they still, although motor, the property of motor is it can have a very high speed, very high rotational speed, but the torque is usually not that large. Especially for vehicle, we usually need a large torque in order to climb a hill or something. In order to climb a hill, usually if you just directly use a motor to drive the car, the torque is usually not enough. So we need a reducer to enlarge the torque. It can reduce the speed because when we climb a hill, we don't really need a high speed. We need a large torque to climb a hill. Yeah. So in that case, we may use a reducer. So the purpose of gear train to change it, to change the output over input torque or the speed ratio. So where do we need a gear train? Well, in a lot of cases, like in a vehicle transmission or in a wind turbine. Yeah, for wind turbine, you see the wind turbine usually rotates with a very low speed, right? But you know, inside the wind turbine, there's a generator. The generator is basically a motor, but you rotate the shaft. And you rotate the shaft, then the motor can generate some power. But if you want to generate large power, usually you need a very high speed. So for wind turbine, it's actually increasing the speed. You see from the external, the turbine is rotating very slowly. But they usually install a reducer, or I shouldn't call it reducer because it's increasing the speed. But they will install a gear train so that they will let the gear train to increase the speed to transmit to the generator. Because the generator needs a high speed in order to generate more power. So, yeah, so we are going to take a look at several different types of gear train. The first one we're going to discuss is the most regular one is multiple external gears. So suppose link 2 is the input, link 4 is the output, then we're trying to find the speed ratio from the input to the output. So I just use the same formula to find the relationship between a pair of gear. So let's start with omega 2. Omega 3 over omega 2 from our previous formula, we know is the teeth ratio, the number of teeth, the ratio between the number of teeth. So these two, they are external gears, so we know it's negative N2 over N3. We can write another equation to express the relationship between gear 3 and gear 4. So it's the same form. Omega 4 over omega 3 equals minus N3 over N4. And right now we want to find the relationship between the input and output. So the output, omega 4 over omega 2, you just time these two up. So if you time these two, you'll find N3 will just disappear. So you only have N2 and N4 remaining. Yeah. So actually this one, the teeth number of this one is not important. Yeah. But it can help us to change the direction. Yeah. So right now, omega 2 and omega 4, they are in the same direction because of this one. Although the teeth number, the size of this one is not influencing the gear ratio, but it changed the direction from the input to the output. Any question for this one? So another example is the internal gear. So I think I'll just write here because the equation is very short. So here, well, it's connecting, let's say omega 3 is the input, omega 4 is the output. So it's connecting from 2 to 3, 3 to 2, and 2 to 4. But we want to see the gear ratio between 3 and 4. So 3 and 2, they are just a pair of external gears. So we'll have the same equation, omega 2 over omega 3 is minus N3, N2. And another pair is the 2 and 4. 2 and 4 is an external gear and an internal gear. External and internal. So omega 2, omega 4. And they are gonna rotate in the same direction. So there's no negative sign in front of it. And to find omega 4 over omega 3, you just time these two up. So you will get omega 4 over omega 3 is minus N4, N3. So you'll find it's still not influenced by the teeth number of the middle one. Yeah. Only the first one and the last one matter. The middle one, they just change the direction, but they are not influencing the speed ratio. And this one is the same as this one, so I'm not going to calculate it. Only we can use these bevel gears to change the angle between those axes. Otherwise, their speed ratio are the same as the external gears. Any question for this one? And okay, so here is just introducing an it's called reversing mechanism. Well, it's just an example. And so I think 4 is the output and 2 is the input. So right now, it's using, so there's a triangular link connecting the 3 gears together. And this triangular link, like, it can rotate a little bit. So there's one mode for this linkage is in this position. Anyway. So in this position, going from input, the link 2, to the output, it's going through link, from input link 2 to gear 3 and to gear 4. So in this case, omega 2 and omega 4, they are going to rotate in the same direction. And we know the gear ratio from our previous case, omega 4 over omega 2 is N2, N4. This one right now, because it's 2, 3, 4, so it's the same as this one. And this one, we know result, omega 4 over omega 2 is N2 over N4. So here, yeah, it's the same. But it put this mechanism, so if I rotate this triangular link a little bit, and this time I remove the connection from link 3 to link 4, and instead of using link 3, gear 3 to drive link gear 4, I use gear 5 to drive link gear 4. So right now it's from 2 to 3, 3 to 5, 5 to 4. So it has one more stage. And this one more stage is not going to change the gear ratio. The gear ratio is still the same, but only the direction is reversed. Right now omega 2 is rotating clockwise, but omega 4 is rotating counterclockwise. So no matter how many gears you add into this gear train, you only influence the direction. The middle, only the first and the last gears, they will influence the gear ratio. The middle one, they are not important actually. They only change the direction. So this example is use multiple gear and use a linkage, so you can do the forward driving and reverse driving. So here comes a more complicated one. So it's still gear train, but right now there's one new thing. So right now there are 4 gears in total, 2, 3, 4, 5. And yeah, we call this compound gear. And in this type of gears, you will see some of gears, they share the same shift. Right now the gear 3 and gear 4, they are sharing the same shift. So when they are sharing the same shift, that means they are rotating, their angular speed is the same. Right now, omega 3 is the same as omega 4. So we still want to see the gear ratio from omega 2 to omega 5. So let's try to see how the gear ratio will look like in this case. So I'll start from gear 2. And so it's in contact with gear 3. So you can still write the same expression because these two, they are just a pair of external gears. So you still have this relationship. And the same, gear 4 and gear 5, they are just a pair of external gears. So you can write a similar form. Omega 5, omega 4. So right now, according to these two pairs, 2 and 3, and 4 and 5, these two pairs. We know their relationship, they are just a pair of external gears, so the relationship is very simple. But right now I'm looking omega phi over omega 2. That's my output and that's the input. So I'm going to expand this one because I need to use these two equations. So I need to expand this one and to include these two terms. So I can expand this one into this form. You can see this form, well, I just add omega 3 and omega 4 into this expression. But these two and this one and this one, they are the same actually. But because right now this one, we have some information about omega phi over omega 4. So I can just put our previous result into this equation. So you get negative and we know omega phi over omega 4, we know omega 3 over omega 2. We also know omega 4 over omega 3 because right now they are installed on the same shift. So their speed is the same. So omega 4 over omega 3 is just 1. So the speed ratio from omega phi to omega 2 right now is more complicated. Right now, every gears matter. Yeah, it's different from our previous simple gear train. Right now in this compound gear train, every gear, the number of teeth of every gear matters. They all will influence the gear ratio. Any question for this one? Yeah, so for this type of gear train, when you are going to analyze it, yeah, you usually need to go to see if you can find some pair of the external gear or internal gears, then you need to go from, right now we want to go from 2 to 5, but you need to go from 2 to 3, you need to find the relationship first, then find a relationship between 3 and 4, then 4 and 5. You need to go step by step. Any questions? Let's move to the next one. Okay, this one is a bit complicated. So right now, there's a gear train. So there's an input gear 2 to 3, 4, 5, 6, 7, 8, 9, 10. Now, a very simple one. Right, so we are trying to find omega 10. Where's omega? Omega 10 is here. And V11. 11 is the linear velocity of this one. So this one, we haven't introduced this one. This one is called a rack. So it's a gear rake. The rack is basically look like this. The rack basically is a straight link, but there are also some teeth on this rack. And when are we using this one? If we want to convert the rotational motion of a gear into linear motion, then we can use this one. Yeah. So this rack is sliding on certain surface. So we can convert the rotational motion into a linear motion. Okay, so let's try to solve this one. So from 2 to 3, 2 to 3, they are just a pair of external gear. They are a pair of bevel gears, but bevel gear work the same way as external gears. So I start from omega 2. Omega 2 to omega 3 is minus 60 over 48. And 3 and 4, they are on the same shift. So 4 and 3 is just 1. Let me put the symbol. And then goes from 4 to 5. 5 and 4. 5 is five is 120, 4 is 80. Then we goes from 5 to 6. 5 to 6, they are on the same shift, so the speed is just 1. And 7 to 6, 6 to 7. External gear, so I put a negative sign here. And 6, 60, and 7, 40. Almost there. And 8 and 7, they are on the same shift. So it's 1. Nine and 8. And 8. Alright, so there's a spatial property I have introduced. So for this shift, let's go back to the previous slides. How can we describe the teeth number of this one? It's not a gear, so it's a bit difficult. Well, maybe you can say, how do you describe it? So we use the thread. Thread, that means how many lines here? How should I say? So thread is the number of the helical curves. For this one is maybe let me draw something on the board. It's more clear. Let's back to our example. So the top one we call it single thread. In this example, it's double threaded. So what's the difference between this one? If you follow this thread, and because at the back I couldn't see it, so I draw a dashed line. You follow this thread. Basically, this one and this one, they belong to the same thread. If you just follow it, yeah, I would say they belong to the same thread. So we call this one single thread. If I rotate this shaft by 360 degrees, by one cycle, this one is got to move one step. This teeth is got to move one step. So this one, the teeth is got to move to here later. So move one step. But for double threaded, actually there are two threads here. So I draw one with a white one, another one is yellow one. But in order to make, so I also install a gear teeth here. If you follow this white one, it's moving from here and it's moving along this white dash line, and so it's going to the next white one. And there's another thread, it's the yellow one. So it's this one. But this time, if I rotate by 360 degrees, where will these teeth locate? If I rotate the shaft by a cycle, by 360 degrees. If I rotate this one by 360 degrees, because this teeth is going to follow this white thread. So next moment, not next moment, by rotate the shaft by 360 degrees, it's got to move two steps. Because right now it's following this white one. So rotate by 360 degrees is moving with this white one. So next time it's going to move here. So rotate one cycle, this one will only move one step. But this one will move two steps. Yes?
How do we know, for example, in 7 and 6, there have
9 and 8. 9 and 8. Or it could be positive or negative, because right now they totally change the direction, so that's why I didn't put a sign here.
So we are just guessing?
No, because it's right-handed, so we'll use a right-handed to decide the direction. So here I will keep the positive or negative. I will not consider positive or negative for now, but I will need to know the direction of the 8. Once I know the direction of 8, then later I will investigate, because the right-handed thread. So I can use that to see how 9 is going to rotate. Okay, if the 8, just according to our previous, this example, because it's, okay, I'll just use this one. Right now, I don't know how 8 is going to rotate, but later I will use those from this first one to this one to find the direction of omega 8. Once I know omega 8, suppose it's rotating according to my right hand direction, then I know according to our previous analysis, if I take a look of this one, this white one, if it's rotating in the white, my right hand direction, then it's going to, next moment it's going to the yellow position. So it's gonna push this gear to rotate in this direction. So I'll use this method to know the direction of 9. But right now I didn't put a positive or negative sign here, because they totally change the direction. They change from x-axis to another coordinate. So I think even if I put a sign here, maybe it's not very clear, because they totally change the plane of the axis.
If you don't have any information, you consider they're moving like clockwise?
If I know the direction of 8, then I can use this method to know the direction of 9. Right now I didn't put a sign because they are on different plane. So I don't know if it's proper to put a sign here. Yeah. Okay, so because right now it's double threaded, so it rotates one cycle, it will move this teeth by 2 steps. So that means it's equivalent to a 2 teeth gear. For this one, it rotates 1 round. This one will just move 1 step. So this one is equivalent to because this one rotates 1 cycle, it will move the teeth by 2 steps. Basically, it moves the distance for 2 teeth. Yeah. So here we just put this N8 equal to 2. Yeah, because if we want to use this one has 80 teeth. This one has double threaded. It's double threaded. So it means I need 40 cycles to make this one to run for 1 cycle. Because each cycle will move 2 teeth, move a distance by 2 teeth. So you need 40 cycles to run, to make this one to run 1 cycle. So that's their gear ratio. 2 divided by 80. So the last one, V, oh, sorry, there's omega 9, omega 8, sorry, omega 10 over omega 9. Omega 10 and omega 9, they are in the same direction. They are on the same shift. So this one is 1. Then the last one is V11. V11 should be the same speed. Right now, I need to consider the radius. Yeah, because the velocity of the link 11, any point on this rack, it can be written as, because the linear velocity of a contact point is still the same for the rack and the gear pair. So the velocity of this point can be expressed as V11 or can also be expressed as omega 10 times R10. Any questions? Let's take a 5 minutes break, then we'll continue to finish this one. So right now, I try to find the relationship between omega 8 to omega 2. Right now I define, because right now this axis is keep changing, sometimes in the x direction, sometimes in the y direction. So I determine this one as positive x, this one is positive y. And it start here, so it start with positive x, positive y. So it start with positive y, and because right now it changed the axis, changed to the x coordinate. And if this one rotating in positive y, this one is going to be negative x. So it's in this direction. Yeah. If this one is negative x, this one is going to reverse. Right? This one, yeah. Positive y, negative x, and this one is positive x. So this one is not x and y, so I just draw the direction, but I didn't determine it's x or y or something. But it's rotating according to my right-hand direction. This shaft is rotating according to our right-hand direction. This one, if it's rotating according to our right-hand direction, then we need to see if 9 is rotating clockwise or counterclockwise. So I'll use the same method. You investigate, you pay attention to a certain point. If it's rotating this way, then this point is going to move up. That means this line is going to move up. So that will push this gear 9 in this direction. And if gear 9 rotating in this direction, gear 10 also rotating in this direction. And so 11 is going to in this direction. Yes?
我怎么知道那个2号是这样还是这样？
你说2号，你说是？
就是它是那一根是绕过它的，还是从正外负外？
哦 right. Yeah, I assume it's this direction.
因为我想说它画过那一根的那个没有虚线，
所以你觉得它
画在上面。
Okay, yeah, that's right. So it's saying because the line here is solid line, so this should be negative y. Okay, if it's negative, then you change all the sign or direction. All the direction should be reversed. But right now I'm assuming it's positive anyway. But yeah, according to this figure, it should be negative. And the ratio will just according to our previous. So we'll see from omega A to omega 2 first. Here I will, yeah, and omega 2, A to omega 2. So a ratio will just be the same way we did for our previous compound gear train. Yeah. So you just expand this one into multiple terms. And because we know the relationship of each terms, we know 8 to 7, 7 to 6, etc. So just put those relationships, those are previous already defined the relationship. So just put those numbers into this expression, and you can get a gear ratio. You can continue to work for omega 10 to omega 2, yeah, by doing so. Any questions? So here we're going to introduce, it's similar to a compound gear train, but we add one more constraint. So previously for those gear train, the input shaft is here, output shaft is here. But right now we are trying to make they concentric. Concentric means the input shaft and the output shaft, they are on the same line, on the same axis. Because that's easier for you to in the real application, it's easier for you to install this type of drive. Because usually we want, for example, if we want to install a gear reducer to a motor, we may install a motor here, and once we install this gear reducer, this one is going to be the new output for the actuator. So they will still be coaxial. They will still be in the same axis. Now I may install a motor here. So the motor, the shaft of motor is still the same as the new output axis once I install this reducer. Yeah, so concentric gear train or concentric gear reducer is very similar to our previous example, but only right now it has a constraint. Right now for this one, you can see there's R2, there's R3, R5, and R4. In order to make them share the same axis, and because right now 3 and 4 already share the same shaft, and right now we also need to make 2 and 5. They are not sharing the same shaft, but they are sharing the same axis. And you can see from this plot, in order to make this happen, R2 plus R3 must be the same as R4 plus R5. So we have one more constraint to satisfy for this gear train. Previously we don't have anything like this. And we know because the radius is in proportional to the number of teeth. So you can rewrite this one as M2 plus M3 equals M4 plus M5. So let's take a look at an example. So in this example, the teeth number is not given. It's asking us to design a concentric gear reducer and to have a train ratio or a gear ratio of 18 to 1 when omega 5 compared with omega 2. So we need to design something that can achieve this gear ratio. So how can we do it? So we will still use the same expression. We'll still find the relationship between omega 5 to omega 2 first. So the relationship between omega 5 to omega 2, I can expand omega 5 over omega 2 into this expression. And we know omega 5 over omega 4 is M4 over M5 with a negative sign here. But because this one will 3 to 2 also have a negative sign, so they'll just cancel each other. And 3 and 4, they are sharing the same speed. Anyway, so we get the expression for omega 5 over omega 2 can be expressed in this way. So this one needs to be 18. So there are several ways you can manipulate the N2, M4, M5, M3 to make this one equals 18. But there's just some limit here. It said the minimum teeth of pinion. Pinion is the smallest gear in this gear train. So minimum number of teeth is 12. So anyway, the minimum among these 4 N2 to M5, the minimum one you can choose is 12. So that's one limitation. Another limitation is no more than 10 to 1 for each stage. What does a stage mean? So for this one, we have 2 stages. We have first stage is from 2 to 3. And 3 and 4, they are the same, so we don't consider them as a stage, or it's just a stage of 1. Another stage is from 4 to 5. So 4 to 5 is a stage, 2 to 3 is another stage. So it's saying we cannot have the stage have more than 10 to 1 ratio. Yeah. So that means let's say if 5 is 12, then 4 cannot be larger than 120, something like that. So one stage cannot be larger than 10. I mean, the gear ratio of one stage cannot be larger than 10. So yeah, for M4, M5, that's one stage. If I decide M5 is 12, because there's a minimum we need to satisfy, then M4, the maximum M4 can be is 120. It needs to be smaller than 120. that's a limitation. And so right now we get this gear ratio, but we know because right now it's a concentric gear reducer or concentric gear train, you need to follow another rule. That's R4 plus R5 equals R2 plus R3. Or I just use the number of teeth instead. So we need to make this one equals 18, but we also need to make this one valid. N2 plus N3 equals N4 plus N5. So you can imagine right now we have two equations for 4 unknowns. So we have unlimited number of solutions. So you can just pick one that satisfies these two equations and also satisfy those limitations. So here I just give an example. You can have more solutions, but here, because it's 18, usually we want those ratio to be integer. So it means you need to divide this 18 into some integer times another integer. For this one, I probably choose 6 plus times 3. You can also try 8 times 2 is also valid because for each stage it's no more than 10. It's still below 10. So this one also works fine. But we don't use this one because for this one stage would be more than 10. This one is not good because it's not within the limitation. So here I'm trying 6 times 3. So that means M4, M5, and make it 6. And 2 and 3. So just trying to decide it. So right now, if I have M4 over M5 is 6, N2 over N3 is 3, then I can get the total gear ratio is 18. Yeah. But because of this, I know M4 equals 6 N5, N2 equals 3 N3. Yeah. And I just put this result into this equation, so I can get a relationship between N3 and M5. So we know another rule we need to follow is all this n must be integer. Yeah, because the number of teeth must be integer. So you can put a random number. You need to make them reasonable. So here, let me start with this one. Because M5, it seems M5 is a small one. Because M4 is much larger than M5. So maybe I'll just make M5 meet the requirement. The minimum number of teeth is 12. So let me make M5 is 12. If I make M5 is 12, then N3 is 21. Then N2 is N2 is 3. Yeah. N4 is and of course you can use any other You can have any other solution, but it's just one of a solution. I pick a smallest one and make it equals 12 to meet the limitation. Yeah. And by this one, I can also get an integer number for n3. And once you get n3 and n5, you can quickly get n4 and n2. Any question for this one? Yeah. So just one more limitation for this concentric gear reducer. Okay, so I think I'm going to let's just take a look at this one. So when do we use this gear trains? The most commonly used case is in transmission, in the vehicle transmission. In vehicle transmission, it looks like this, and there are several, because in the manual transmission, you have different shift, right? You may want to make the vehicle to run with higher speed, or sometimes you need lower speed but higher torque. So when you use the shift to change the speed ratio, the most traditional manual transmissions, back to the, like this. When you change the shift, you just mesh different gears. So you can have different gear ratio from the input to the output. I think we'll have more examples. Yeah. So here is using multiple pairs. It looks like all of them are meshed right now. But actually, right now they are not all working together. They use a clutch here. So the clutch can engage the gear to be fixed with the shaft or not. So although right now it looks like all of them are meshed together, but not all of them are working now. Only this one. Back to this one. So right now there's an input and it's going through this bunch of gears. You can choose one of them. So it's an input, that's the output. And right now you are engaging different pair of gears. So sometimes you may engage with this one, there's one gear ratio, and this pair is another gear ratio. This one is another gear ratio. Yeah. But not all of them, right now they are engaging. Only one of them will be engaged. So for example, maybe use a clutch. So the clutch will decide if this shaft is solid connected with the gear. So only one gear will be clutched at one time. So right now it's inserting this one to clutch. So right now it's converting from this one, and it will go this one and to this one. This rotating speed of right now it shifts. So right now it's engaging this one. You can see the velocity of this one is the same as the velocity of a shaft. So although all the gear they are meshed together, but this pair, right now they are just freely rotate by themselves. They are not influencing the output shaft. Yeah, let's see again. So right now it's engaging the last one, and these two, they are just freely running by themselves. So this one is engaged with the shaft. So you just use a clutch to engage these three gears to change the speed ratio. For this one, all the gear they are engaged, but you can just for right now, this one and this one are loose. So this pair is not working, this pair is not working, only this one is working. So it goes from this one, this gear, they have a certain ratio, and it can make this shaft to run, and this shaft to run will make this one to rotate. This one rotate will also make the last gear rotate, and this last gear will bring the shaft to run with the same speed as itself. And next time if you want to change your speed, you just lose this one and engage another one, and you can have another speed ratio. Another commonly seen transmission is not using gear. It's using, we call it CVT, continuously variable transmission. So it's basically formed by a pulley, a pair of pulley. So right now, anyway, one is the input, that's the output. Right now, this input is using a belt to connect this pair of pulley. So if you see the pulley from the front view, it looks like this. So if you see this, this one's a pulley, this one's a pulley. If you see from the front, the pulley looks like this, but the distance between these two, it can change. So you can imagine if they are closer, if I make them closer. If I change the distance between these two pulleys, this belt is not to be pushed outward. If it's pushed outward, that means right now this one has larger radius. So by using this way, you can also change your gear ratio. So you can take a look at this video. Right now it's in this position, but later you'll put an actuator to change. It's explaining. Well, right now, this one is, this one has smaller radius. Right now, this one has larger radius. But he'll put an actuator to change the distance between these two and these two. And by doing so, it's like the one I draw on the board. I put the air pressure to push these two. Right. All right. I want to fast forward. It's very quick. Okay. So it's on, you just put an actuator and to change the distance between these two. So you can also use this method to change the speed ratio. Although it's not gear, but it works somehow similar to gear. It just uses two wheel or two pulley with variable radius. and to change the ratio. And by using this one, we can change the speed ratio. For the previous example, the manual transmission, we also have some fixed speed ratio. But for this one, we can have continuous speed ratio. I can change with the distance with a very tiny difference and to slightly change the ratio. Yeah, so that's it. It's similar to a gear train, but just use different mechanism to achieve the speed ratio. Okay, so the last one, well, this is the most important one actually, is a planetary gear train. I don't know if you have seen something like this. So it's it's a simplistic planetary gear train. It includes several parts. One is a central gear, and it's an external gear, and also a planet gear. We may have several planet gear. In this case, we only show one. But you can have multiple. You can have multiple planet gear surrounding. They will all have the same size as this one. But you can have multiple here. The reason to put multiple planet gear is to share the load. Yeah, to make the loading is more uniform distributed. Yeah. So, and there's an arm here. Arm is connecting the sun gear, the central gear to the planet gear, connecting the center of this one to this one. Yeah. And there's a ring gear. Ring gear is an internal gear. So we usually use this type of expression to represent a planetary gear train. So this part, there's a sun gear. I hope it's imaginable. There's a sun gear, and this one is a planet gear. And because there's a shift, there's an arm connecting from the center to the center of sun gear or the ring gear. So this one is the arm. This one is like a side view of this one. Yeah. This one is the front view, this one is the side view. And this one is the arm. Arm is connecting from the center of planetary gear to the center of either the ring gear or the sun gear, because the ring gear and the sun gear, they share the same axis. Yeah. And this one, maybe I can draw. This one is the ring gear. It's just a simple representation to represent a planetary gear train. And there are many different variations. This one is the simplicity and can have more. So for this one, you also have a compound gear train within this planetary gear train, and this one has multiple compound gear train. Yeah. So we are trying to analyze the motion of a gear, or planetary gear train. So usually for regular gear train, we only have 1 degree of freedom. So you provide an input and you will get the output. You provide only one input and you should immediately get the output. It's just 1 degree of freedom, so you only need to provide one input. But for this gear train, for this planetary gear train, it's actually a 2 degree of freedom system. So usually we need to fix something first. And once you fix 1 degree of freedom, then you only have 1 degree of freedom remaining. Yeah. But originally, if you didn't fix anything, it's a 2 degree of freedom system. And here I have a pair of model, you can take a look. I didn't bring it. Anyway, I think it's in my office. I have a 3D printed. I'll bring it next time. Anyway. So that's this one is also a planetary gear train, but right now it doesn't have a ring gear. Let's back to this one. Because this one is somehow similar to a concentric gear train. So there's also a equation we need to satisfy here. If you just take a look at this geometry, there's a sun gear, radius of sun gear, maybe I call it RS. There's a radius of planet gear, I call it RP. There's a radius of a ring gear, I call it R. If you take a look at this one, these three parameters, they also need to satisfy an equation. That is R, radius of a ring gear must be the same as RS plus 2RP. Yeah, according to the geometry, you need to satisfy this requirement. Yeah. Otherwise, you cannot assemble them. So 2RP is the diameter of the planet gear, and RS is the radius of a sun gear. The summation of these two should be the same as the radius of the ring gear. Yeah. So that's the basic formula that the planetary gear need to satisfy. And for some planetary gear train, we don't always have a ring gear, or sometimes we may remove the arm. Yeah, but it should still work anyway. So here is just an example. It's the planetary gear, but without the ring gear. Yeah. But I still have a sun gear, has a planet gear, have an arm, have another sun gear. Right now it's like, yeah. So right now this arm is connecting the center of this gear 3 and gear 4. And another point is connecting to the center of the sun gear. But C and 2, they are rotating with different speed. You can see there are dashed line here. That means they are two different parts. So they are coaxial, but they are not having the same speed. So there's omega C, there's omega 2, and they are different. Okay, so let's try to. So right now it's providing two input. One is omega C. Omega C is the speed of we call the arm, sometimes we call it crank. So that's why we represent the C. The C is crank. Stand for crank. So right now it's providing a crank with minus 150 RPM. Omega 5 is minus 50 RPM. And we try to determine the speed of omega 2. So before I do this one, I will start with this simple one first, our original planetary gear train. And yeah, then we'll expand to this one. For this one, let me try to write its relationship first. Right now I'm introducing a new expression. So I have this omega 2 and with c here. That means if we considering the speed of 2 relative to the crank, so the c means it's relative velocity or relative speed. So you can imagine if consider this c as a fixed arm. Then what's the speed between 2 and 3? If we are considering the crank as a fixed bar, then the speed, the relative speed of 2 to c and 3 to c, they are just the gear ratio, the number of teeth, the ratio between the number of teeth. It's just a regular external gears, similar to a regular external gears, when we consider c as a reference. Yeah, because right now c can move, so it's a bit different from our previous external gears. But right now I just introduced this new expression, omega 2 with respect to c. So it means imagine this c is the reference, and you are have a speed of link 2 over c. And this omega 2 over omega 3 with respect to c will still be the number of teeth, the ratio between the number of teeth. Any problem with this one? So if I consider c is a fixed link, this one should be valid, right? If c is not moving, you can ignore the ring gear for now. Just look at this two. If an arm is fixed, then the speed ratio is just n3 over n2. But this one is a relative speed. It's not the absolute speed, because 2 will also move corresponding to the motion of c. So the absolute velocity of this link 2 should be omega 2 c plus omega c. It's just similar to previously you have something like this. BBC is, sorry. Previously we have a velocity, and this VB, absolute velocity of VB, can be relative velocity plus the velocity of the reference. And right now we are doing the same thing. This is the absolute velocity, but right now it's a rotating velocity. And it's equal to the relative velocity or relative speed plus the speed of the reference. Yeah, so that's just an analog. There's for linear speed, there's for angular speed. So right now we need to find the, so basically that's it. And because eventually we may need to find the speed, or we may need to find the absolute velocity. So I can change this equation. According to this tool, I can change this equation to omega 2 minus omega c. Because eventually we will need the absolute velocity instead of this relative velocity. So we'll change to this form. And previously I mentioned this one is a 2 degree of freedom system. So we need to provide this system with 2 inputs. So usually we'll fix one of them. So maybe in this example, it's providing 2 speed. Well, but this one is different from this one. But right now, if we just take a look at this equation, there are 3 unknowns: omega 2, omega c, and omega 3. There are 3 unknowns. So if we need to solve this one, that means we need to provide 2 input. Because right now it's 3 unknown, but only 1 equation. If you add 1 more input, that means you eliminate 1 of the unknown. But right now 3 unknown, 1 equation, so we need 2 more conditions in order to find the solution. So that's why we say it's a 2 degree of freedom system. You need to determine any 2 of them. You either determine omega 2, omega 3, then you can get omega c. Or you determine omega 2 and omega c, you get omega 3. Yeah. You need to determine 2 input in order to get the output. Otherwise, you will just freely run by itself. Yeah. And these 2, the T's number are unknown. Those are unknown. Yeah. So for the rest, I will record video, and probably you just go online to check a video by yourself. And yeah, so that's it. I think this one is our last in-class lecture. So for the rest, I'll post it online, and please go online to watch them by yourself. Okay, and sorry, I didn't have time. So here is your quiz. And yeah, you can come to pick it up. Quiz number 2, and we'll have quiz number 3 next Monday. Yeah.